And now I'd like to ask Professor Greg Baiden to resume the podium and tell us about mining off-planet. Thanks, Greg.
It's interesting, you know, to begin to mine off the planet, you have to figure out how to do it on the planet. And one of the things that I wanted to go through a little bit was finish off a little bit of what I had yesterday, talk to you a little bit about undersea mining for briefly, so you can get a feel for what's happening in the world today. Go over a scenario that we planned as part of what we were doing for the CSA work. The scenario was the piece of work that enabled us to do the CSA work. And so we'll show a few pictures about that, and then end with some breakthroughs that are going on and some of the research that we're doing that enables that to be a reality. I didn't really put this slide up first yesterday, but I wanted to put it up today. I had the good fortune of running this project called the MAP project. And it was a project that was about a $30 million project with partners from all over the world, some from Scandinavia, some from Canada. And one of the things that happened was I got my PhD for developing a telecom system that minimized latencies into the underground operations. And that allowed us, once we had that technology, to begin to look at teleoperated mining in a real way. What was interesting was our delays were down below 1.5 seconds in latency. That allowed us real-time control as deep into the mine, some of the mines as 8,000 feet, and from far away as Toronto up in the mines in Montreal, which were 800 kilometers away. But it was a $300 million research program that involved many engineers and scientists, of which I got the chance to lead. Most of the work hasn't been published. It's unusual to be a professor now and everybody wants to hear about what you published, and most of that work was kept inside of drawers. Although when I did get to leave the company, I was able to work on that technology and can show you all this stuff now because it's part of what I was allowed to do. So long-distance teleoperation was really at the heart of what we learned how to do, and at the very heart of that were telecommunication systems. The other major important piece is how to locate yourself inside of the rock. And I'll talk a little bit more about those today. Technically, what we're doing isn't called automation or teleoperation, it's called automation. And that's what the Japanese have coined the phrase. And what that means is automation with the human touch. It's a word that I didn't know about until I started working as a professor. But what it really means is one person can run multiple machines because you involve them in what they're good at, and you involve the systems in what they're good at. I went through this yesterday. Telecommunications network are the key to this, positioning and navigation. Process engineering, monitoring, control. A lot of that's turned into what do teleoperation stations work like and look like. The mining methods, which I won't show you today, but which I showed you yesterday in some of those graphics. And then the dollar signs of being able to do this. Mining equipment becomes the key, as well as systems that monitor the health of all those machines. This radio frequency network is kind of an unusual thing. Some people in Canada at a mine called Brunswick had done the first part of this communication system by getting the head in and using broadband technology. They had put it in the mine and hardwired the mine to various sensors. But what it came out to was, could we build a device that would fit on there that would allow us to run over radio, and in our applications use what's called leaky feeder cable to allow us to leak the signals out into the mine tunnels and use them as a guide. After about 3 years of work and pretty extensive work in Fishkill, New York with IBM and in Boca Raton, we came up with a network that allowed us to do this kind of work. The network had a capacity of 750 megabits per second, which allowed us to move real-time video and things around. An important point was that we had the entire radio frequency spectrum available to us, because the minute we went 10 feet below surface, the FCC and in our country the CRTC have absolutely no jurisdiction. So we can go in and use that radio frequency spectrum at will for whatever we wanted. And that was the big advantage of what we were able to do. That work culminated in the creation of a company called Automated Mining Systems, which I was the president of while I worked at INCO. And its job was to build these distributed antenna translators. That's what a DAT stands for. And for all you guys that come from the world of your rock bands in the back of your car, this wasn't any digital technology. This was pure RF plumbing. And I had a hard time finding people to do it, because everybody had been taught to work in the digital world and didn't want to work in the RF plumbing world. But that's what made it work. Then the second thing that we did was this unit here called the Horta is a very unusual unit. It's actually a plan system. And I'm going to tell you the story about it, because everybody's laughing, and they should be. The Horta was developed as a plan system for howitzers in the battlefield. And the reason for the development was a howitzer crew used to be a 4-person crew. 2 of them were surveyors, and 1 person drove the turret and 1 drove the gun. Quickly, the opposition in that military engagement found out that if you shot the surveyors, the howitzers were no longer useful. So some people at MIT got together and created this unit called a plan system, which sat inside the howitzer tank carrier and eliminated the need for 2 people and increased the firing rate from 45 minutes to 45 seconds. What was interesting about it was that this ring laser gyro was so accurate that we started to look at them for using them for positioning underground. We had a number of very significant problems to solve, which may be of interest to everybody here. One is that we found out that the equations inside of the unit were actually off. What happened was, as you moved inside of the Earth's crust, you eliminate layers of the Earth's crust, and so the gravity constant changed. And this particular unit had gravimeters in it, and as those gravimeters were in there, they started going off and getting skewed. I came back and told the people at Honeywell that was a problem. And I was just a dumb old miner to them, right? So what would I know about aerospace and all those things? And so they said, no, our Hortas work perfectly. Our plan systems work perfectly. And I said, well, they actually don't. And I have a graph that shows you how much they go off for each 500 feet you go down into a mine up to 8,000 feet. And they said, oh, no, it's not right. And then about 9 months later, I got a panicked phone call from Honeywell asking for the graph, because I guess they needed to be used. But the unit, we weren't allowed to get a full unit because of the implications. And I had to sign all kinds of stuff with the U.S. Department of Commerce to get it. But in doing it, the stripped-down version, they wanted to find a way to make the Star Trek Horta acronym work for this unit. So Horta stands for Honeywell Ore Retrieval and Tunneling Aid. And if that isn't a bad way of getting an acronym, I don't know what is. So anyways, as we progressed with it, now that we had the unit be able to tell us accurately where we were underground, we started putting relatively inexpensive laser scanners with it and putting it onto vehicles like the one you see here in the picture. This was in the mine that I ran at INCO, which was a research mine. This particular miner is doing surveying work, which is what you would typically not see. You can see the Horta mounted in the center of the screen there. He was collecting 300 hertz of points as he was going, which was a phenomenal rate in comparison to what surveyors could do. And that allowed us to create these kinds of tunnel maps that I showed you yesterday. We took the ability to survey from a 4-person crew to accomplish the task that you see in front of you here over a 9-month time frame. And we were able to do that entire piece of work within 2.5 hours. And so it was a phenomenal change in surveying productivity, to the point now where that's a marketable product for our business. We just finished a 30-mile long survey of 2 mines that we joined together. The estimates for the work manually were $5 million over 3 years. And we went in and did that entire surveying work in 1 month and did it for a fraction of the cost. And so we are out now and doing this all over the place as part of what our business is about. I want to talk now for a minute about mining technologies. This particular tunneling jumbo that you see here was a jumbo we bought for our research work. It actually ended up getting fitted with one of those Hortas and was able to move into the face. And this particular video is the first time that a crude avionics system was put onto a piece of mining equipment. And so this machine not only went in, and you can see in this video in the corner that as the tunnels begins to turn around, the operator was actually lining his booms up to the face to be square. And he could position those booms within about 1 inch of where they needed to be from surface. And so he was sitting in a surface control room doing all this work, which typically had to be done by people going there. That was quite a breakthrough for our business, and still is quite a breakthrough. And what you see in that video has yet to be duplicated in the mining industry again, except for the work that we're doing in our company. This is another interesting project. These 3 drills would typically be operated by one person per drill. And the fleet at the mine, because of the inefficiencies of travel time down into the operation, was 5 prior to us doing this work. This particular guy now is sitting off-site 30 kilometers away from the mine and 2,000 feet above surface, and he's running those 3 drills that are distributed in the mine. When NASA was first trying to get an idea whether they should drill on Mars, a number of people came up from NASA, and I don't know exactly where, to visit this at my site. And they came in and were completely amazed that you could do this kind of work over those distances. We've taken this whole unit and moved it as far away as Montreal, Canada, and drilled up in Sudbury. And we had people come in, like Mark Arnault, and sit down at the controls and run these machines. They are still in production after 12 years, and they still continue to work every single day. The lag time to Montreal was 1.72 seconds. We also did the teleproduction where we had machines like this, and pretty well everything you see in the world today around this kind of equipment has evolved out of this research project. So what the people are doing in Australia and Africa and various places, the suppliers that worked in this business had ended up working on this project in one way, shape, or form. This video is quite interesting because this caused quite a stir inside of our company. Rick Bertrand, who's sitting here, he's actually running 2 machines at the same time, but they're in automatic guidance as he moves from one machine to another. The interesting thing about the video is he's actually at 2 different mines. So he's sitting in a control room running one machine at one operation that's 26 kilometers away and running another machine at another operation that was almost 40 kilometers away. And he's switching back and forth at will. And I told you the story yesterday about the Star Trek transporter. That's what my boss wanted. He wanted to be able to hit a dial and have the skill of the person and the machines just flip. And so literally we flip by computer network from one place to the other. In all this, I got to create what was at the time the very first operations center in the world. It was very small. It had 3 mines connected to it. The research mine that I ran, which was the 175 test mine, and then 2 fully operating mines. Danny Hillis came up to see the work I did and came walking in and said to me, you realize that you're doing more teleoperation systems simultaneously than anybody has ever done on the planet, including me. And I said, I didn't know that, but thank you very much. But this project that I'm going to show you, and I only have this one little video clip around that kind of epitomizes it, is the control room we built. And in this control room, there's 7 different pieces of equipment being operated by 7 different operators. Now, when I say 7 different pieces, I mean 7 different types. Some of those pieces, the operators are running 1 or 2 or 3 of each one of those types in this video. And so all along, you have everything from delineation drilling or diamond drilling through to production tunneling drilling, through to production drilling, long hole drilling. This guy's running an LHD scoop tram. The guy beside him was running a spray-on machine, very similar to some of the spray-on coatings that people were talking about earlier today. And all those machines were all running from that surface control room simultaneously over the networks we built. And we had room on those networks to run another 60 or 70 machines simultaneously. It started us down a path inside of the company and now inside of Penguin at looking at putting operation centers distributed around the globe. So that now you would have an operations center that's linked by telecommunications to each one of the head frames, and the people would come to work every day in one of them and only work for their 8-hour shift, and control would be transferred in 8 hours of time zone apart to the next control room and around. Now today you'll see in the mining industry over the next decade and a half, there's going to be companies like Rio Tinto that have already started to put these operations centers in, where I've gone in and consulted with them and explained all the things they have to do, and they're now implementing it. What it does is it allows us not only to run mines, but it forces us to get really a lot better at doing our mining engineering software systems. Today, mining software is nowhere near the capability of what anybody in this room is used to. They really are very, very bad, and they need to be improved a lot. Employees always work day shift. What it does is that if you look at the costs of mining today, for every bit of aluminum or any bit of what you see on the table, about 65% of the cost of that is labor. And so if people want to have lower cost cars or lower cost whatever, we have to figure out how to get that labor component cost down so that we can make those units, those pieces of metal more cost effective. Now I want to switch gears. I've done some consulting work in the last little while, and I wanted you to see this because I think there's a lot of parallels between what we're about to do in underwater mining and what the space industry has to do as they go forward. This is a black smoker. This is an active black smoker. And you'll see as you look at this video that eventually you'll see some animals around the outside of that black smoker. Those animals are consuming sulfur. They live in an environment where they convert what we would consider waste and pollution, and they eat it and thrive on it. And so we have a great deal of interest as business in looking at going to these places, because if we could find out how all that works, then we would probably be using these processes in our processing plant to eliminate pollution. The other interesting part of this is that if you actually want to go and mine there, once these black smokers seal over, you can go in and get extremely high-grade nickel, copper, platinum group, gold minerals. And you can mine them like you're foresting as opposed to mining. And so I got this video that I wanted to show you. This company is out of Brisbane, Australia, and I just did some work with them over the last couple of years. They're now opening up this new deposit in Papua New Guinea and looking at how they're going to do this work. This is now a new mining ship, and this ship is under construction today. What's happening is that they're looking at how they put a shaft through water and pumping systems down into the operation. One of the things in mining is that the term sunk cost came out of the mining industry, because when you sink a shaft, that large amount of money is sunk. What's interesting about this is you don't have sunk costs because you can pull all this back up, so you completely alter mineral economics. These units are now being built, and you'll see this. This is like a little road header that's being lowered down to about 2,000 meters underwater to be able to go after that abandoned black smoker area. There's a bunch of interesting issues about this, because as people build this kind of technology, the reason they're in Papua New Guinea is they're within territorial waters. That's the only way that they can mine, is within territorial waters. And the legal regime that comes with this is if you move off of that, you're into the middle of the oceans, which isn't any different from going to the moon. Somebody needs to figure out who's going to own what so that people can go there and mine it. One of the interesting things we're working on, which I'll show you near the end of the presentation, is some underwater wireless wireless communications technology, because they're looking for swarming robots to be able to do their geologic interpretation. Once this stuff is pumped, they just barge it to a smelter and begin to smelt the minerals that they're gathering. What's interesting as well about this is that where we would have a deposit that may be kilometers and kilometers long to get the same metal value out as what you're able to do here, the size of this ore body is roughly the size of an American baseball field. And they're going to produce a large percentage of the world's copper out of this very, very rapidly. Their waste to ore ratio, these guys will mine 2 million tons, where most of the surface miners will have to mine 20 million tons to accomplish the same metal objectives. Now I want to talk for a minute about space mining. Brad and myself and another gentleman, Louis Grenier, who worked at the space industry, or at CSA, came up to our research center in Sudbury. And Louis spent the better part of about a day and a half trying to convince me to write a strategic plan for mining in space. Because I kind of sat there saying to Louis, I got lots of work to do, and I do all this work in the mining industry, and I do not have time to consider space. And could you please go away? I don't want to do this. And anyways, as you're about to see, he convinced me that I should do it. What we began to look at was, given what we had done in teleoperations technology, I'm quite comfortable today in saying that I can run machines with 3 or 4 second delays in them. If you start talking about any longer than that, I start to get concerned. But I can see how to do it with the level of automation and the level of work. Telecontrol rooms on surface with teleoperator chairs, which we build, are a regular event in what we do. And then Brad showed me a lot of the work around the lunar South Pole, and we began to look at some of the things that we might want to put in there. The next few slides are kind of a backup, which is kind of what I would call a scoping, almost a scoping level study that we would do in mining, that we basically pulled off to be able to do this. First of all, the map technology that I just showed you, they meet the basic fleet has been tested and is technically feasible. It is not space hardened, and it won't be space hardened until somebody wants to do it. These concepts are being applied around the world today, and the techniques that we're using form the basis for what we would look at as being a lunar outpost and an underground mining operation. In what we did, some of the assumptions kind of went like this, and you have to remember this was done, what, 2 years ago now, Brad? Something like that. So we made an assumption that there's a large concentration of H2O found trapped in a crater, likely at the lunar pole. That we didn't know whether that was true, and we talked about that probably for a week to are people going to believe this? Are they not going to believe it? Basically, the rock types on the moon aren't any different than the rock types on the Earth. They'll have the same compressive strengths, the same tensile strengths. 1/6 gravity, which for miners, that's a huge deal. That is probably the biggest deal that you could imagine, and we have to go through and really think about that. We assume that no water would be available for initial operations, and no atmosphere would be available during initial construction of the lunar base and the mine. We assume that you would have a small-scale nuclear power plant installed at site. Just so you know, as I talked to you before about the James Bay site, there's going to be an 8-megawatt power plant installed, all diesel gensets, although Stuart Brand has got me contacts for people in the United States to get some quotes on doing it a little differently. We assume that the value of water in low Earth orbit is substantial and that a market exists. Now, that was an assumption. Transportation of equipment and commodities is available at a reasonable cost, and operating personnel initiated construction operation from Earth at a lunar mining teleoperation center. So the requirements are that we had to have that lunar mining teleoperation center, lunar power, the equipment supply and transportation, an airlock on the side of the crater. We assumed that if you put an airlock in there, you could run a mine just as if you were on Earth. And it wouldn't be very difficult to do once you put an airlock on. Everything would work as if it was here, as long as you provided that work. We also assumed that you would have a high bandwidth telecommunication satellite established in orbit, as well as the kind of optical communication systems that I'm about to show you would be in place locally to be able to run these machines. You only need 5 basic machines to do this work. I put 4, I don't know why. One is a delineation drill, which is essentially a small-scale diamond drill. What that does is drill in to find out where the ore is. A development drill, which is what you would use to be able to drill the holes to create the tunnels. Some form of digging machine, an explosives loading unit, and a sintering machine, which is similar to our ground support machines that we would use today. We assume that you'd be on the ground, you would have something that looks like this, which are an artist's concepts of the kind of teleoperation workstations that we're used to making. People would sit in there with some feel for the machine with tactile feedback, and the screens allow you to get the best view of 3D type operations without having to increase the bandwidth that you need to transmit. 4 basic machines. The upper one is a digging machine. You have a dump truck, a spray-on machine, and this unit combines the drilling and explosives unit into 2 booms on the unit.
What's the size base?
Interestingly enough, I think, I'll say it to you this way. If you tell me how much you can launch, I'll make them work. Because it's not that hard. It really isn't. I mean, big scale mining machines today are 36 tons. I can make a mining machine that's 20 tons. I can make a mining machine that's 18 tons and it'll still work. And so you tell me what launch capability you have, and we'll make the machines that you need to do the job. Initially, you would have to tunnel in a little bit into the side of a crater. We would like, as miners, to do as much work overhead as possible, because if we don't do it overhead, we have to bail the cuttings of what you do with the rock. And that's a tough thing to do in a zero gravity environment. But if you can drill somewhat overhead until you get inside, then you should be good. And so this shows a unit that was drilling and then now removing the material. We would begin to put some form of airlock in place, and you notice the way the airlock's built with wheels on it, something that's launchable and something you could put in and then seal around, but the machines would still fit through the center core of it. some form of sintering machine, which would sinter the rock to protect it. There's a lot of rock joints in current mining, so we do a manual support with drills and mechanical bolts or spraying on shotcrete or something like that. I would assume that the moon's no different.
How much maintenance do you need to account for dust?
I don't know. I mean, I've heard. Is it Harrison Schmidt who talks about that? I've heard him, and yeah, I've heard lots of that. I mean, I come home, if I've been in a mine, I come home every day full of dust, and I'm kind of used to it. If I've been at a coal mine, that's just part of what we do. And I mean, I do understand, and the realism of a lot of the particles are charged, so they stick in a different way. But we'll try and we can deal with it, I believe.
There's also less dust issues after you pressurize the road.
Yeah, absolutely.
It's only very column that you have to worry about.
Another issue is this stuff is all very, very cold, right?
Yeah.
And how do you
Rock breaks better when it's cold.
Okay, this is going to be super cold.
That's okay. It's still rock, right? Like I realize, like I don't mean to belittle it, right?
What I'm saying is it's going to be difficult to keep your machine warm enough.
Yes, that will be an issue.
I don't understand the argument that air would help the dust. It seems like it makes it worse.
That doesn't suck.
Well, why don't we let me finish my talk and we'll have that debate, because that one could go on for a while. What we initially said was that you would start off with an underground caves that you could work from using hydroponics and other things. That, so you know, is a regular occurrence in most mines. I've been in the mines at Creighton. We grow mushrooms, we grow trees. Interestingly enough, we do it because we don't need pesticides. We have people that live in refuge stations all the time. You know, those 33 guys who were trapped lived in a refuge station for easily 33 days, and their only real problem was they didn't have food and water. That was the real issue down there. Could they eventually get out? They could eventually get out if we could find them. The miraculous part of that rescue was that we found them, because usually mine layouts and underground tunnels aren't where they say they are, which is why some of the work we've done with these positioning systems is so remarkable for our industry. An initial outpost we had looked at as well, putting in things like where I come from, I helped to build the Neutrino Observatory in Sudbury, and that Neutrino Observatory is down at 6,500 feet underground. We use special coating materials on the sidewalls to make sure that the rock would withstand and water wouldn't enter. But the more we talked to that about with physicists as we were doing this work, the more interested they got at having these kinds of astronomical observatories on the moon. And could we make this kind of thing a reality in an underground tunnel? And the short answer is, once you have those 4 pieces or 5 pieces of equipment, you can do pretty well everything you want. The other thing that's important to say at this point is that if you have those same few pieces of equipment, you can continue to grow this base ad infinitum in the rock. So as you talk about colonizing somewhere, you would just keep on growing underground as you went forward. We had laid this out with bunk beds over here, over there, and then put plants all through that we would bring up, as well as lunchroom facilities, and we had scientific research stations or research offices in this as well. All that, and you see that little blue dot up there. I'm going to show you a little bit more about that in a couple of minutes. We looked at how you would apply different types of mining methods. I showed you that video yesterday. This is just a cross-sectional view of the same thing. What we do is we make little honeycombs in the rock and then try to let itself break. The big problem on the moon is going to be gravity. and how much we would have to spend to allow that to break. But it does work in pretty well all the rock here on Earth. All of the biggest mining companies in the world today are using this method, and that's how they make their money. They come in and undercut these big operations, and they do very well. There's a lot of others that are using other methods. I would argue today with that some of that is dependent on the ore body they get, but the ones that seem to have moved into mass mining in this way are the ones that are making money. So, as an economic outlook, a lunar commercial mining forecast, the space exploration costs must be balanced by the revenues. Future customers for lunar-derived commodities will extend from lunar surface outposts to orbital transportation and emerging manufacturing centers. You can't have a manufacturing center without raw materials. The moon represents the discovery of a new continent of unexplored land and has a significant mineral potential. The one advantage of gravity is that the moon actually has more mineable material than the Earth, which is something that isn't quite understood. We can only go here on Earth because of the way that things work economically to about 5,000 feet. There are mining operations that push that, and there's some that go as deep as 13 or 14,000 feet, but the bulk of them are around 5,000 feet that are underground and above. This isn't the conclusion of my talk, but this is the conclusion of this report. Teleoperated terrestrial mining will be gradually applied worldwide. The space industry can build on the capabilities being developed in teleoperated mining techniques. Our Smart Step proposes the construction of an underground outpost to provide humans with a safe haven in the moon, free of environmental hazards, with the bulk of construction occurring telerobotically from Earth. We were proposing at the time in here an analog site to test the concepts or teleconstruction of a lunar outpost. Now I want to show you a little bit about some of the breakthroughs that we've been working on in terms of research. You saw that other work we did before around using ring laser gyros. We've been working quite hard in my research in the university on what I would call subsurface avionics systems. The idea of being able to take a planned system and put it with a GPS equivalent was where we started. And we, at first, didn't believe that we could build something like that. We had a large mining company by the name of Rio Tinto come to us asking us if we could solve this problem. And it's funny, these projects I get into are the same as the one with the space agency. I told those guys to go away. I didn't want to work on this. and the reason I didn't want to work on it, because everybody's tried to do this. Like, they've tried to locate trapped miners, they've tried to, and finally, after a little while of thinking about it, we came up with an idea that we're now patent covered for pretty well around the world, because Rio Tinto's covering the patent costs, not me. But the idea was to put in, and this picture's right out of the patent. The idea is to put in 3 very low frequency satellites embedded in the rock. And then with those satellites embedded in the rock, to come up and use the atomic clock and the calculations for distance and velocities to be able to determine where any one of those dots are inside of that rock mass. What we've been able to do so far, and I didn't think I'd have time because there's like 3 presentations on this alone, but we've been able to accomplish that in the lab. We're now quite knowledgeable, and we think we'll be able to locate those dots within a meter, with the antennas being kilometers apart. We're about to test that in Australia, coming up just after Christmas. And Rio Tinto has a particular application for it. The application has been to stop the arching and hang-ups in block cave mines. the first part of it is I didn't want to work on it, but the other part I did. I lost 2 very close friends in a bad accident where an arching occurred and the whole arch came down and compressed all the air. It came out of the tunnels and blew their Jeep about 300 feet down the tunnel. And they were killed instantly, fortunately. But it's because this particular method needs this technology to be able to do it. And miners tend to push the envelope on some of this stuff, and those guys knew what they were doing, and that just happened. The idea is shown in this slide as well. Basically putting rocks in and letting, and I mean, probably the best way to describe it is if you think of the movie Twister, and they tried to get all those little balls into the tornado to measure temperatures and pressures and humidity. We're trying to accomplish the same thing, but inside of rock. And that's the first application of this very low frequency underground positioning system. Then I want to talk about a different subject. And it was interesting that John, where's John Mankins? It was interesting that John started talking about orbiting space solar power, because Paul Verbose got me to a meeting down with John 10 years ago, I think now. And Paul knew about all this work that I was doing, and he wanted me to get involved. And I heard the debate about whether, somebody put up in their slide, we shouldn't telerobotically construct the orbiting space solar power. Whether you do or whether you don't, one of the things I did was got to work on how you would actually run robots in orbit telerobotically. And one of the biggest problems was finding an alternative to radio communications, because you couldn't put something up there with radio communications because you'd take the whole bandwidth, the whole frequency spectrum to do the work. So we began, and it's interesting because it wasn't just John and Paul. It was also mining companies who were trying to mine at extreme altitudes in the Andes, and Nautilus, who wanted to mine underwater, and people inside of my own company after I left, trying to mine extremely deeply in the ground. All those required us to work in an aqueous environment, and I can explain each one of those, but I don't have time. The idea that we had was to build a new wireless optical cellular communication system. I started, and some people told me I was crazy and it was a dumb idea and I shouldn't work on it, and I heard lots of stuff. But the idea was to be able to address some of those communications issues, make teleoperation more widely available for people, and then begin to develop the concepts around it. So the idea was that you would flash light on and off. And I was back probably in one of those days when I was looking at my old little fiber optic light where the ends came out, and said, geez, if you just turn those on and off rapidly enough and you could receive that signal, this would work. So we built one. Well, this is actually probably prototype 7 now. And this was built to go to a test for General Electric. General Electric was quite interested in them because the fuselage of the new jets you guys are making actually flex, and they didn't have a way of putting a high bandwidth backbone down the center of the plane because you would break all the wires as they went. So we were able to get 20 megabits per second over this unit. Interestingly enough, we were able to get it underwater. And I chose to work underwater only because I was trying to limit the communications that I could watch and observe how this would work, having no idea that underwater communications was at best a few baud. And I ended up at a show because some people at MIT asked me to go, and a whole bunch of people from Electric Boat started going crazy, and I was like, what's going on? I don't understand. And I said, you have something that goes faster than like a few bits per second underwater. And then Darlene came, she got me into trouble as well. We do this picture because you can't do all the photography underwater the way I'd like. But what these are the LEDs are moving on and off at about 40 megabits per second. This guy's moving the joysticks and turning the motors on and off. And he's getting video feedback from the front of the submarine, which is, you can see the camera. All that's being done optically. There's no radios involved. And so we've been able to file for patent and get the patents around the world to do this work. It's a very, very secure form of communication. Now, remember back, one of our original goals was to try and do this for mining. And so we went down and we did this little guy in a different color light, and you could see stuff in the back with his teleoperations center working as well. And so we've been able to translate this to a number of things and continue to work on it as we go. There's a whole bunch of really interesting business opportunities around this, like tsunami warning systems in the Pacific that gliders need to go to that currently hover around them for months, and we can transfer the data in no time at all. And then the last one I want to talk about is a problem that kind of got me involved in the Chilean disaster a little bit. I had a friend from a mining company by the name of Extraterrestrial come to me with a problem, and they had a huge mine where the crown pillar was collapsing. And what that basically is the piece of rock across the whole mine which keeps it secure. When that happens, you have to shut down the mine if something goes that badly. So they had this crown pillar collapsing, and they had this other problem that there was a 100,000 liter propane storage tank on the collapse zone. And so, I mean, if that was down here, does that qualify as a rocket if that goes off? It must, eh? Anyways, the problem was they needed to go and get it, but they had to be able to look at it from underneath to be able to see if it was stable enough to put bulldozers on it. And so to do that, you had to go down through the portal and travel 1.5 kilometers into the mine that had been shut down. No people were allowed to go in because of air blasts. The ramp was washed out with 3-foot ditches in it. The ventilation potentially was going to be non-existent, or methane buildups. And could you go down and do this laser scan for us, Greg? I tend to take on these weird problems, eh? So we got to work, and we built these 2 machines in this teleoperation center. The machine on the far side is basically a communications hub. And it's an electric 6-wheeled robot that will run for about 80 hours. It goes down and sets itself up with a 2.4 and 900 megahertz and a 2.4 gigahertz system on it for long distance transmission. And then the second robot goes through and links to the other robot for localized control, all while being done inside of the trailer by 2 teleoperators. Pretty severe environment stuff to try and accomplish. We are now we've done our first initial test where we've gone about 600 meters into the mine. The robots have come back out. We've done all the work we said we were going to do. We have the last phase. The miners didn't tell me how straight the tunnels were, and so my line of sight communications weren't line of sight because mining tunnels are never line of sight. I should have known that going in, but so I have had to go back and get a few more telecommunications tools to be able to accomplish the task. But we've been 600 meters in, and all the systems work flawlessly, and now we're just getting the final equipment to do the final inspection. And then the last one I want to talk about, and it's only a schematic, but I want to say to you that we've invested $10 million of work in the mining industry of a project that I led called guided drilling. And essentially what this drill is a miniature mole that drills rock. In our industry, one of the problems we have is keeping holes straight. Geologic formations cause our holes to deviate, and we want straight holes to load explosives into to get proper fragmentation. So this drill was conceived by a team of 20 engineers that I led. And the idea behind it was to eliminate the need for drill steel so that we could put it in with an umbilical, and it would be a miniature tunnel borer. This looks like it's not real. There's $10 million been spent. Prototypes exist. All the IP is in my hands. The units have drilled with individual components for, in some cases, for up to 3 million feet of drilling. We've used some really fancy technologies that mining guys would typically never use, i.e. Some guys came in and told me they were going to glue some things, and I said, you're going to do what? Because we tend to work in the metal business, not in the connection of things through gluing. And it turned out that that was the thing that did 3 million feet of drilling. And then they told me that Boeing, or whoever they bought the glue from, was from the new 777s. They're probably not new now, so I don't keep up with them. But they told me that it had failed prematurely, which I kind of went, really? That's pretty good for prematurely. Anyways, I believe that that drill is of significant importance, and Brad and Chris have told me that the ESA has been putting out stuff that's similar to this. But we hold all the patents in that field and hold all the prototypes, so I'm kind of interested to see what it is they're putting out. Because in the world today, there were 3 of those projects in that kind of technology. One was being done by Shell, one was being done by myself at Inco, and another was being done by a Norwegian drilling company. And those are kind of the key 3 organizations that could accomplish that task. So anyways, with that, I want to thank you, and if you have any questions, I'll try and answer them, and we can maybe have the debate about dust. Thanks.